Good morning, student. In the series of abstract algebra, our topic is quotient and ideal. Myself, Dr. Govind Sharma, Assistant Professor in Mathematics. Now, today we will do the some important concept of quotient and ideal. Earlier, so I move to the our lecture. In previous lecture, we will have already discussed about quotient. Quotient is the ring. Let R be a ring and I any adder add then the structure R upon I having the element this type where A belongs to R and I is idle of this also R upon I will show the properties of so R upon I for example each card okay क्वेश्चन और इसी को हम बोलते हैं रेजिड्यू क्लास रिंग ऑफ रेजिड्यू okay? So element how it behaves that I plus A plus I plus B I plus C for the addition operation and for multiplication dot product I plus these are the two operations. Okay, I is identity any idle. The part is identity for this ring. So A and the inverse element like plus minus A plus I plus so I plus A minus A is equal to so we see that I plus 0 or we can say I is the identity element and each element of have inverse element so R upon I is first order. then it follows the homomorphism and the kernel of is defining home, and then we have done some important theorem based on quotient ring, based on quotient ring, like every quotient ring, like some remark or we can say important theorem, that every quotient ring is homomorphic image of a ring R is homomorphic image of R, and every idol of ring R is kernel of homomorphic. This is important theorem, that quotient ring is always homomorphic image of R, and every idol of it is kernel of homomorphic. Second theorem, fundamental of every homomorphic image of a ring R is isomorphic to some quotient. So some quotient. So every homomorphic image of a ring R is isomorphic to some quotient. Next, we will do another theorem. This is the fundamental theorem. This is called the fundamental theorem of fundamental theorem of isomorphism. Now, today we will do important theorem, that theorem third statement, an ideal I of a commutative ring with unity is prime if R upon I is an integral no. True. An ideal I of a commutative ring with unity is prime if R upon I is an integral domain. So let us assume that I is an prime idol of commutative ring with unity. So R upon I is also, let us assume that I is a prime idol of commutative ring. We have to show that an ideal I of commutative ring with unity is prime if R upon I is an integral. And here we will show that R upon I is integral domain. For integral domain, we know that we will show that this is without zero divisor. So we take first I and prime ideal of commutative ring. Okay, so R upon I is also commutative ring with unit. Now we will show R upon I is without zero divisor. Let I plus A plus N I plus B belongs to R upon. Okay. So I so I plus AB is equal to implies AB belongs. A belongs to I or B belongs. That means I plus A is equal to I or I plus I. That means we are saying that I plus AB is equal to I. We will show here that R upon I is without zero divisor. We take two elements from here. We will show that here in two elements multiply is zero or identity element if one of them is zero or both are zero. Okay. So we take I plus A and I plus B multiply by both multiplication give us the I. So I plus AB is equal to I by the multiplication. So AB belongs to I. That's right. For A belongs to I or B belongs to I. Because I is a prime matrix, so this is not a composite. So this is prime. So A belongs to I or B belongs to I. Then so I plus A is equal to I or I plus B is equal to I. One of them is right. So we can say I upon R is without zero divisor. So R upon R upon I is integral. Conversely, let R upon I is the integral domain. Now we will show I is prime idol of prime idol prime idol. Ah, if this is integral domain, then we will show that this is prime idol. Here, to go through the convert that R we take R upon I as integral domain. Now we will show that I, the ideal is a prime ideal. Then if it is prime ideal, then R upon I is integral domain. Then we will show that R upon I is a integral domain. Then show that I is a prime ideal of R. For this, we have the two elements from I. Now we will show that because R upon I is an integral domain. Integral domain. So there does not exist zero divisor. Even let A B belong R, A B belong. Then we will show, then we show when we show A belongs to I or B belongs to. Okay. Now Now AB belongs to I. That means we can say I plus AB is equal to 1. I, because it's an integral domain, so it has not zero divisor. So I plus AB is equal to I. So we can write A plus A, we can write like this, A plus A plus B, dot product of is equal to I, or I plus A is equal to I, or I plus B is equal to I. A belongs to I. That means R upon I without zero divide. So I is and prime. So I is a prime. That means the conclusion of theorem is that if R upon I is a prime idol, sorry, I is equal to I, R is equal to I is integral domain, then I is a prime idol. And simply if I is a prime idol, then R upon I is a integral domain. So very interesting result. The result should be remind. We can say the result of this theorem is important. Many competition exams ask the true and false result. We can write here that R upon I is integral domain if I is prime. And both. I should write it. Okay. Now, the another theorem, an ideal, an ideal I of a commutative ring. Commutative ring with unity CRU is maximum. Maximum. If and only if the quotient ring R upon I is if the an ideal I of a commutative ring with unity is maximal. If I is the maximum ideal, then R upon I is equal. This is also very important. Actually, I want to tell you that the results are more important. Is theorem in Quotient ring. Given that R is a commutative ring with unity. So R upon I is also a ring. So and it consists I and I plus E identity. Given that R is a commutative ring with unity. So R upon I is also commutative ring with unity and it consists I and I plus E identity elements. First, let me assume I is maximal ideal. Maximal ideal. So I plus A is not equal to I plus 0 is equal to if you differ element or A is not belongs to I. If A generates by A, then I plus A is ideal of then then A I plus A. Okay, I plus A में होगा और ये R में होगा. Now and and I is maximal ideal. Given that we assume that I is maximal ideal, so I plus A is equal to R, or R is equal to I plus R dot A. I belongs to I. R. Now E belongs to R, then I1 belongs to I, or R1 belongs to R. That means E can be write as I1 plus R1 dot E, E minus R1 dot E. implies I1 belongs to. That means E minus dot belongs to implies I plus E is equal to I plus R1 dot E plus plus we can write like that because the operation of quotient ring by the operation of quotient ring. So that means I plus A is inverse of I plus R1 that belongs to R1. R upon I also consists each element inverse. So, so we can say, or if a ring, a commutative ring with unity has multiple inverse, then it is called field. So here we see that if this is a maximal ideal, I is a maximal ideal, then it has a inverse element. So we can say inverse element multiple inverse elements. So R upon I also consists each element inverse. So we can conclude Egypt. Okay, we do again this. I explain again. This is important theorem. So an ideal I of a commutative ring with unity CR. We can say CR is maximum if and only if the quotient ring. So here we take R is a commutative ring with unity. R upon I is commutative ring with unity. So I and I plus E This is for addition. This is for addition and this is for multiplication the arity element of it. So if I is maximal ideal, so I plus A maximal ideal, so I plus A is not equal to I plus 0 is equal to I. A we take another element, it's not in the I. So A generated by A, A ideal generated by I plus A is an ideal of generated by, so A is not in A, I, so I in I plus A and I plus A in, so I is in maximal ideal. Or this is the property of maximal ideal. Here we show that how it is may behave in maximal ideal. Now R, we take R as an element of R, I plus R. E belongs to R, so I belongs to I and R. Because element of this type, I, E belongs to, so this is R belongs to R. So E minus R dot A minus dot A H belongs to I. So I plus E, I plus R dot R, 1 dot A is also in I. So this can be written as like this, and this means I plus A is inverse of, so R plus I also consists inverse element. So here we write a result that if A is equal, if I is, so here we assume maximal, then we prove this. Now we take R upon I is equal. No, now we will prove that. Now we will prove that R upon I is equal if I is maximal. Now we take I is a maximal ideal if R upon I is equal. So now we move to our some questions are waiting for us. Which is the true? Question. If CR is a division ring wrong, if quotient ring is called ring of the reduced, right? Right. A ring with zero divisor is called integral domain wrong. Only B is the right option. Which is the operation of quotient ring? I plus A plus I plus B is equal to I plus AB, where I is the ideal and AB belongs to R. Today lecture I use this many times, and I dot A multiply I dot B is equal to I star A. These both are there. So A and B are the right answer. First, which statement to R upon I is a ring? Abstract. Z plus B integral domain right. Z2 is a field. 3 are right. So ABC option are right here. Only D is wrong. Which statement is not true? Isomorphic image of a ring is not isomorphic image of a region with division. This is the right statement. B is the right statement. That pipe is a field. This is also a right statement. Isomorphic image of a field is field. This is also. So only A is the wrong statement. But in the question, he is asking about the what is not true. So A is the answer. Option A is the answer. Which statement is true? F A plus B. This is not true. One home onto homomorphism is called isomorphism. This is true. This is true. Acid is orthomorphic to acid. That is also true. And finite ID is a field. This is also. So three are B, C, D are the right option. Question. I hope today we have the important theorem. So revise it and just tomorrow we will again discuss the remaining part of the theorem. And